Hello, my name is André Beleza, and I'm a PhD student in the M&M group at Institut Néel Grenoble, working on the Heat4Energy project. Every day, industries generate enormous amount of waste heat, energy that simply dissipates into the environment unused. This wasted resource has the potential to be harnessed, providing power without relying on conventional fuel sources. From data centers to manufacturing plants, low-grade heat is everywhere, but existing technologies fail to efficiently convert it into usable electricity, especially for small-scale applications. Imagine a world where small-scale sensors, remote monitoring systems, and other low-power devices run entirely on waste heat. No batteries or external power sources, just energy that would otherwise be lost. But how can we turn this untapped power into something useful? Converting even a small fraction of this wasted heat into electricity could make a huge impact, but current methods are either inefficient, costly, or impractical. And that's where the Heat4Energy project comes in. Heat4Energy is developing a new way to harvest low-grade heat using thermomagnetic energy conversion, where materials change their magnetic properties with temperature, generating electricity. This could revolutionize waste heat recovery and energy efficiency. My research within Heat4Energy focuses on thermomagnetic materials by producing compositionally graded thin films through sputtering with the use of different targets made of different elements and alloys. In this way, we can systematically alter the chemical composition across a wafer, like this one, and we are able to fine-tune the thermomagnetic properties of different materials and study them in a high-throughput way. That is, create a big spread in composition and therefore material properties in one singular wafer, and employ automated and fast-paced measuring techniques to measure and analyze up to 300 points per wafer. Like this, we can analyze the thickness across the deposited film using a profilometer, the chemical composition by utilizing the scanning electron microscope here behind me, the magnetic properties of the material using different magnetometry techniques, a scanning book system, which is based on the rotation of reflected polarized light, and even determine the crystalline structure at each point of the wafer in a quick instant at a synchrotron. In parallel, we're developing freestanding thick films and micromagnets for small-scale thermomagnetic generator prototypes. Our goal is scalable, efficient thermomagnetic generators integrated into real-world energy systems. Even small improvements in waste heat recovery could lower emissions and reduce energy costs. But beyond industry, this technology could power sensors, wearables, and off-grid devices, functioning indefinitely without the need for batteries. By unlocking this additional energy source, we can move closer to a world where low-grade waste heat becomes a valuable resource rather than an environmental burden. Follow our progress and see how we're changing the future of energy.